Okay, let's start our session today. So today I want to, last class we were discussing surface networks. I just want to make you aware that that problem can also arise in downhole networks, okay, on in-well networks. So I want to make just, I hope it will be short, but let's see, downhole networks. Then we are going to talk about so it's like an introduction. We are going to use later we are going to talk about a bit about ESP design. Okay, so just like we talked about compression, we are going to talk about let's call it flow design. Okay, because there are many things in ESP. We are not going to the construction part, the manufacturing part, just the flow design. But before going there, I want to go and use the opportunity to talk about flow of undersaturated oil and water in pipes. Okay, and just something that you probably have covered before, but it's just the new element, which is the how do we use it in our calculations, and there is a very specific special phenomena happening when you have oil and water. Yes, so let's downhole networks, they can happen um, um, in what we call multilateral wells. Okay, those wells that for some reason you have maybe different branches. That's typically done to increase the recovery factor to use less wells. And then you have that basically because you might have that the wells have different length. They are perforating through different formations. The water oil contact on the gas oil contact might be different, so they are going to be producing, typically it's not that all of them produce exactly the same. All of them will produce slightly different. So in that case you have a network of all of these branches, and actually what the approximation you can make is that they don't interact too much, each branch with each other. And you can make just like using an IPR equation. For example, if you're using this this equation, okay, the linear PI equation, okay, that each one of them will behave like a separate well. But you see, to know how much you want to produce from each one of them, you are going to produce from each one of them, you still have to make a network computation. Also, so that, let me put it here a bit better. Multilateral, you can also have it in multi-layer, where you have, for example, you have one formation, you have another formation, shallow, medium, and deep, and you have your tubing, and you have some packers isolating your, and then what you make, you might have a valve, or you might have just an opening, you might have a sliding sleeve, you might have all kind of so I'm going to put this as a box to make it more generic. Okay, just like a box. And this box, it can be just a simple opening. It can be also a a sliding sleeve. Okay, something that all of you know, sliding sleeve? No? Um, well, I can show you. Okay, you have the tubing. You have some holes, and then those holes are might be initially covered. You have no flow from the annular area to the inside of the tubing. But with a tool, you can just actually shift that sleeve. That sleeve has some, like a collet. It's like, I think I have a better figure below, but that keeps it in position. So just by moving this inner part, you can decide if that section will be closed, you won't be producing from that section, or if it will be open. The locking mechanism is something like that, has some fingers that they either contract when they are, not, there is not a groove on the wall. The groove is this one, okay, this guy here, and then after it meets the other groove, it's going to expand and lock in position. So that might be, so let me put maybe that figure here. Wait. In Cambia, you just have a normal opening. I have a sliding sleeve that I can, let me put here a comment that I can control. I can decide, shift to open or close. Okay, they have different mechanisms. Sometimes I can do it with wireline. Sometimes I can do it with a tractor. Sometimes I can use this. Now it's very common to use balls. So I send balls inside our friends at Driller. Maybe they have more. They can give us more details. Or you can also have a downhole valve. Okay, and in which you can control. In that case, you need to have a hydraulic line that goes together with the. Okay, I have to put a line, and then I can exactly control the position of that valve. Okay, I can control, and I have different settings. Instead of having just open or close, I can have. And the way it is done, let me see if I can manage to sketch it. So here you have the opening. Usually you have it. Yeah, and on the inside you have, first you have one section which has a lot of holes. Okay, that's going to give you less restriction, and then you will have a higher rate. Okay, then you might have another part which has, for example, only 2 holes, and then you have more restriction. And then you have one part which has just maybe 1 hole, okay, and then you have much more restriction until you reach the part where you have actually no holes, okay, and then it's blocked. So you can decide by moving the inner sleeve. This is just very similar to this configuration. By moving the red part, in front of the opening, you can decide if to have a very big pressure drop, no pressure drop, no flow, etc. Okay, and this is called sometimes it's called an inflow control valve. Okay, and just like in the problem you saw, yes. I have a question on this sliding sleeve. Okay. Once it is locked into place, how do you move it? You can use a tractor. It depends on the. I think I have another figure here. Maybe I can put it. I'm a bit rusted in completion, but let's see. So that's the tool to shift it down and up. And this case is using wireline. And so let's see, the way, imagine that's in the well and that's located vertically. So you lower the tool is going to engage here on this groove, and the blue part is going to be locked in place. You start lowering it down, and then this part you see you have a spring. After it goes through, it is going to deploy out, and it's going to latch on the outer shoulder of the red part. And then what you have to do is you have to hammer up with the wire line. And then that's how you shift it from this location to the other location. And I think I maybe have. Okay, so that's to shift it up, and to shift it down is a similar process, but you have to do the jarring down. Okay, you have, instead of pulling it up, you have to pull it down. Huh? Well, you have in the wire line, you have some weight that you lift slowly and then you drop it. Lift the wire line, you pull it up to jar up, and then the weight down, you just pull the weight out and then you jar it down. Okay, it's called jarring. But if you have a well which have, if this is installed in the horizontal section or very deviated, you cannot use wireline. You cannot depend on the weight of you cannot depend on gravity. You have to use a tractor. Okay. Yeah, so let's see. Let's it just in case to avoid confusion. Yeah, for those of you who are going to work in completion in the future, that's a fascinating area with a lot of tricks and mechanisms. The thing is to get to understand all of them, okay? To understand the principle. But with a wireline, really, you can just make the operation. You can just pull up, or you can just drop it down. Okay, so you have really, with this jarring process, you have to do everything inside the wellbore, just vertical movement. Okay, so but these are not based on that, but they are based on because you want to have control. It's like a choke that I want to control. Okay, but it's not a continuous choke, but actually a discrete choke. Okay, a choke which has only 4 positions. So these ones usually they have a piston here. That so how do I draw a piston? Okay, just a cavity where I inject the line, the hydraulic line, and then if I push, so let me fill it with, in a very simple way, okay? So I fill it high pressure fluid, and then that expands and then moves it, to another position. And I need to have that line in place such that I can close it, open it at will. Actually, we have here one in the lab, so maybe after Easter, we can take a trip to show you how it looks like. Okay, so we have these things that and then we can control. Basically, it becomes a network that I can try to see how much I want to produce from one zone or the other. Okay, and that's especially important when I have, for example, I have a very strong formation, high pressure. Okay, high pressure and maybe low perm. Again, here I have a formation which has, let's say, low pressure and high perm. Okay, so if I don't have anything here to control the flow, it might happen when the well is shut in that I actually start getting that the strong formation will start charging the low pressure formation. Okay, so I get some stealing in production from the low pressure reservoir. Okay, so also be aware that we have also some dual tubing completion. Okay, in which we have exactly the same. We have one formation, then we have another. But actually we put one tubing will be for this formation, and one tubing will be for this formation. Okay, and the two tubings, they go all the way to the wellhead, and then if I am on a platform, it's like I had two wells from the same hole. Okay, and in that case, that's not really a network, but that's basically I can treat that almost like if it was two separate wells. So let me put just here are usually not networks. So I can model that part if you're asking the future to say, well, I have this very complicated completion with 2-3 tubings, and I have to make then you think, oh, it's complicated, it's a network. You can just basically model it like if you had 3 separate wells, and all of them commingle to the same point. Okay, so let me put here we have only 2. So okay, and another thing, okay, before, another warning I want to give you is like in long horizontal wells. Okay, sometimes they can be treated as a network. For example, we can take okay, just here we have I don't remember exactly. I think I was doing okay, imagine that we have an oil well completed on an oil layer, and we have an underlying aquifer. That the same thing can happen if I have a gas cap. Okay, and if you remember, what drives the flow from the reservoir to is just the flow in one position that I name I is going to be just proportional in a way to the difference in pressure between reservoir pressure and this bottom hole pressure at that particular location. Okay, but the thing is that the pressure also along the wellbore has to be higher. If I plot here pressure WF versus the length, put it down. Okay, so here the pressure has to be higher, for example, and then be reduced towards the heel. Okay, that's what I call the toe of the well, and here is what I call the heel. Okay, so because of that, actually what I have the profile, I made it a bit, let me make it a bit nicer. Okay, so actually the rate, if I plot now the rate, I'm going to put another color. The rate, actually, I will have the reservoir pressure, let's say someplace here, okay, up, PR. So really you will have a rate here that is much smaller because the driving force, it might be, small. That difference might be small. But after here, we'll have more and more rate. So the rate goes in the opposite direction. Basically, I have smaller rates, and then I start having more. I will put it maybe like that. Okay, and that can happen if you have what we call a well which is restricted by the um, by the size of by the hole, okay, by the size of the liner. You can also have it in if you have different, if for any chance you have a difference of permeability along the well. Okay, if you have, for example, some reservoirs, like that's the case of troll, you have different layers. The wellbore is going through different layers which have different permeabilities. Okay, if you remember here, also the rate depends on a factor, a permeability, a J. Okay, if we are talking about a liquid well, and that J is a function of permeability. So if you have one streak, for example, which has high permeability, you will tend to produce more from that streak than another one where you have a low permeability. So for those cases, I can make also an approximation depending how different they are, how different is the flow. I can approximate my well by a network, okay, in which I just make exactly the same thing that we made. Okay, just make some points where we will have PWFI. Okay, and in each one of them we will have an inflow. Okay, and a QI. Also, not only in that's a horizontal well, I haven't put anything inside. Okay, sometimes to correct that issue, to allow the well to produce more uniformly, because if I allow that well to keep into production, I'm depleting more this area than that area, right? So what might happen in the future, if I will have a breakthrough of water towards the well, and then I will start producing a lot of water, and then I will have, an increase in water cut that I don't want. So what I make to try to equalize, to try to balance and make it more even, that rate profile, what I make is actually I install some packers in the well. Okay. So I have the same hole, it can be open hole, I can use a liner, I can use a casing, cemented casing, whatever. So let's put our oil formation. Okay, now I know I'm aware of that issue. Okay, I know, for example, I have a very long, this horizontal section, some wells it might be 4 kilometers. So I put inside a tubing and I separate using packers, such that I can control exactly what will be the pressure, or I will control exactly what will be the pressure of each one of these segments. Okay, and for example, if I have, let's say the permeability is more or less uniform, and then you will have the pressure will be here higher and here it will be lower, then you have to put something in between. Okay, if I make holes, for example, here I will put many holes. Okay, and while here I will just put one. Okay, and I can regulate in that way. I can try to make it more uniform. I can try that the rate that is entering into the first section will be the same as the rate entering into the other section. Okay, here, not sure if you can see the holes from there, but okay, and you make it artificially. You make it such, you create a network in a way, and that's also something that you have to analyze using using a network type approach. Okay, this is not actually, we don't make holes on the, we could make holes in the tubing, but actually we use something called ICD. Okay, inflow is called inflow control device, or we can use sometimes ICV, which is the one that I explained before, inflow control valve. Okay, or we can use sometimes AICD, which are autonomous inflow control device. Okay, the first one is just basically what I was painting here, just holes, but of course in a way much more sophisticated. You have to put it on the well, has to cost money, so Schlumberger and Halliburton have to make it expensive, so make money, right? Okay, if you see here on the drawing, you have let me put it, I'm not that tall, so I have to put it here to my level. Okay, so first the fluid goes to one mesh that is supposed to protect from entering sand and from plugging, okay, the hole. Then it goes to flow along the pipe, and then it's entering to a hole. Okay, exactly what I was painting before. Okay, and the size of the hole or the number of the holes that you put depends on where you are. If you are here, you will have less holes, or the diameter will be smaller, and if you put it there, you will have more holes, or the diameter will be bigger. Okay, you have some other types, more fancy, which these are the same thing, enter through the mesh, okay, through a mesh, and then here you have some helical passage in which the fluid is supposed to lose energy and then comes at the end through the hole. Okay, different types, different ideas, different inventions, but the same principle. Inflow control valve, similar to the one I already showed before. The problem is when you have a long, you have many sections. If you have, for example, 50 sections, 70 sections is not unusual on a well. So how if you want to control each one of them individually, you should have this hydraulic line from the top, okay, which is not feasible for. Okay, you will need too many holes on the tubing hanger. Then you have this autonomous, and I think I had. Yeah, let me just put here just the diagram how. Okay, so here, okay, here remember we have a box, right? If we have a box, I prefer to put it like that, so it's like more schematic. And here you have reservoir pressure. Okay, or you can also, if you have this case, you can have, it will be, okay, you just add another component before entering into the wellbore. You have PR, okay, then you have one component which is the IPR, and then you have another component which is the ICD, and then you reach finally the WPFI. Okay, so you have, it's like exactly co-current. Okay, that's why I think that concept is so powerful. You just, to reach the point, you have to know what do you have in between. It can be flow in the reservoir, it can be flow in the pipe, it can be flow in this orifice, but you have to know what do you have to overcome, what the fluid has to overcome to reach that point. Okay, and you can have many things here, many complicated completions, but I think if you think about those terms always, okay, you will try to find a way to make an analog. And in this case, I'm making like a line type analog. Okay, that's for the ICD. Okay, the AICD, just that you're aware, is a new technology. that I think it came a few years, maybe 2004 something. That it's so let me again try to paint it. Okay, and here you have, so that's the wall. That part here is the reservoir. Okay, you have your mesh and you have whatever to avoid sand coming in, and then you have the wall, and inside here you have the inside of the tubing. Okay, and the thing is that if you have the principle how this works, well, actually here I should have something, right? Otherwise it's going to close. So very smart on my side. Okay, so I have a no-go shoulder. Okay, so if I'm flowing here, for example, with oil, this device is made such that it will remain open. Okay, the moment I flow with something different than oil, that is either water or gas, it will tend to create some sucking effect and it's going to close. It's going to choke. Okay, it's a bit difficult, non-intuitive to believe, but I will try now in the break to bring the very simple a demonstration tool that I have in my office, okay, to show it. But basically, when you have oil, it stays like that, but when you have water or gas, it will just go and it will tend to choke. Okay, it will tend to stick to the top. Okay. Yeah, I think that's all I wanted to say on the. So be aware of downhole networks. Sometimes you have to make that analysis. One tool that is used normally for analyzing downhole networks is called Net Tool. I think that's a product by, I think it's Halliburton. Drillers, no? You haven't heard of it? I think it's Halliburton, or I think it's Halliburton, not Weatherford. But it's for analyzing downhole networks. Okay. So now let's go. We have still 7 minutes to the break. So let's go and talk about. Let's talk a little bit about pressure drop calculations. Something completely different. Okay. So pressure drop calculations for undersaturated oil. Okay, plus water. And how does the equation, of pressure drop, how do you call this equation to calculate pressure drop when you have just, incompressible liquid? Yeah, you learned a long time ago in kindergarten, I think it was, that you were 5 years old and they were explaining you that when you have a point 1, a point 2 Bernoulli equation, right? You say that the energy is conserved between 1 and 2. And you could say that the energy that I call H in 1 will be equal to the energy in 2 plus delta H of the losses, okay, the pressure losses. And the energy in 1, what was that? How was that defined? Is if we call here elevation, okay, set 0 reference, so that will be set 1 plus P1 over gamma, which was the density times the gravity plus B1 squared over 2G, right? That will be equal to Z2 plus P2 okay, and then comes the losses. How do I express losses usually? This is kindergarten theory, so you should know it by, I wake you up in the middle of the night and you have to tell me the equation, okay? Is that correct? Yeah. And then I had some other type of losses. So that's due to friction. Here, here. Where is density here? Which this one? Which one? Well, I'm going to leave it like that and ask, and later we see if it makes sense. But let's see, if I want to sum this term, right, with this term, they should have the same units. If I put the density in front, it doesn't have, right? So we will see now. And then you have the other time of losses, which are divided by 2g. A coefficient, not permeability, but a coefficient that I can change. That's called localized coefficient, loss coefficient. Okay, so first I want to call to your attention like two things. So remember we wanted, if we had a pipe, right, we had 1 and 2. Can we do the same thing? Okay, can we have, remember we had 3 ways to calculate, right? So calculation modes were, if you remember, I keep P1 fixed and calculate P2. Yes? And I have P1 fixed, I have the rate, and then I calculate P2. How that curve is going to look like? You're getting, I'm brainwashing you, so that you can, okay? It's going to go like this. I have P1, I want to calculate P2. Is the available pressure, right? So it should be like this. Okay, number 2, P2 fixed. Then I give the rate, and then I calculate P1. Okay, exactly the same. I just have to clear, and this is the equation we're going to use in an exercise we're going to make in class, or you are going to make also in class tomorrow. Okay, we're going to use exactly that equation. Now, there is something important to note about that equation. If you see that velocity, right, is the rate, and which rate is that? That rate is the local, right? The local volumetric rate. Okay, that means at the particular pressure and temperature conditions. And remember, the one that we are using for everything, for all of our calculations, network, field, etc., we are using the standard conditions rate. Okay, that's the one that we are using, and for water also. So that means that I have to, if I have the standard rate, I have to convert to this local rate to make my calculations, right? To make my pressure drop calculations. And that's divided by the area, okay? So how do I convert from local conditions to standard conditions? I have a factor called BO, right? PT, that it will be the rate at standard or local? Local. P and T divided by the rate at standard conditions. Okay, so that's the way. If I have a way to calculate that BO, I have, before to make my pressure drop calculations, I have to convert, and I have to use that rate to calculate that expression. Okay, and I have the same for B water. That is not much, but I also, can take it into account. Now there is another thing. So that means, remember, what is the variation of the PO with, how is the shape of BO with pressure? Something like this. Is it? Yeah, for different temperatures. That's for a temperature of the reservoir for different temperatures. That point here is what? The bubble point, right? So if we say temperature, pressure, sorry. Yeah. Okay, so we are looking at that temperature. Let's say that we're going now, that's temperature of the reservoir. Now let's go for a lower temperature called 1. So how will it look like? No idea, right? I don't remember. I'm trying to get out of the trouble by asking you, but I don't remember. So I think it's something like this. Okay. If Curtis was here, he will, probably be very angry because I don't remember. But okay. So you have P bottom at reservoir temperature, and that will be PB at temperature 1. Okay, so you have to use the right. Remember, because when we are flowing in our system, we are actually going from a reservoir pressure, let's say that is here, all the way to a separator pressure. So we are going to change, the BO is going to change, and also the especially on that region, that's what we are discussing. So the local rate is going to change, and that's the rate I have to use to calculate the velocity. Also, something else very important. How you see density? Density is also a function. Okay, density is also a function of pressure and temperature. Okay, what else? If you remember, what is this F a function of? F is the friction factor, right? And friction factor, if you remember how it looks like, versus something called Reynolds, right? And the Reynolds is density, velocity, diameter. Again, we are divided by density. Okay, so this one is going to change. We already established that. This one is going to change. We already established that. But also this guy is going to change, the viscosity. And that's a big issue we are going to see right away for oil and water system. But how is that plot? How does it look like? Remember, a straight line. And you see, laminar never happens. For very heavy viscous oils, it can happen. And then, okay, something like this, right? Okay, where these curves are for different. You have to make memory. Okay, different roughness. Okay, relative roughness, which is the roughness of the pipe divided by the diameter of the pipe. What happens here? Why for gas was not a big issue. We were not concerned about, why using calculating the Reynolds number, why we didn't have this complexity in gas. Gas usually is very turbulent, so it's always in that region. The friction factor is not a function. How do I put function here? I already used, is not a function of the Reynolds number. Okay, it's only a function of the roughness of the pipe. So that's how we can make that assumption. Okay, so let's we already reached. So let's take a break, and when we come back, we continue why do we care about this old equation. Okay, so let's see. So one of the oh, we didn't find this from Curtis. Okay, so one of the things is that you have to make, when you make calculations for undersaturated systems, you have to make it in a discretized manner. Okay, so the first thing is that because of the pressure along the pipe, okay, then the rate will change. Okay, the rate will change, the density will change, the viscosity will change. Okay, thus you have to make it in a stepwise manner. Okay, so that means that if you have a pipeline or a flow line, or you have a well where you want to make your calculations, you have to make it in a discretized way, and that's what you're going to make later in an exercise. Okay, remember, we always like to have exercises so you can not only hear me talk here in class, but you can also practice and see if what I'm telling you is correct. Okay, so here you have certain pressure and temperature, you calculate the properties, you approximate, and then you calculate the next point in the pipe. Okay. Then here you again estimate once more properties, and then you move in the pipe further. Okay. And that's the process that you. So pressure drop calculations. Okay, and this can be in the well or in pipes. Should be done okay in a stepwise manner. Oh yeah, sorry I didn't show you, but okay, so here is a bit difficult to see, but you see thing you have in a video. Okay, so it's here you see that's a inflow control valve. Okay, here you see the collet, which is okay. Here you see the collet, which is supposed to hold it in place. In these holes that you have in this group, it's supposed to open and latch it in place. This is one that has a hydraulic line to move it. And if you see further, you have the opening. Okay, the opening is there. Okay. See, I say too much. Okay, I think so. Okay, but you have the holes on the inner pipe, and then you have there the opening. So if you want to use, let's say this, you have not so many. Okay, so it will be a medium pressure drop. So if you want to use medium pressure drop, then you have to put those exposed on that part. If you use it now, it will be in the closed configuration. Okay, and that we have if you want to, let's see if we take a trip down. And here you see you have the hydraulic line that comes out to such that you can control the position of the. Okay, here is the hydraulic fluid coming in. And this part is just when you have the it's a long thing. Okay, so we have to make in a stepwise manner, and like you probably know, we have so let's make another page here. We have, so that's the plot that we use. Remember, that's the Moody, okay, or the Colebrook friction factor. Looks a bit nicer than what I made. And you have a lot of formulas. This is taken from actually Wikipedia. Okay, you have a lot of formulas for the friction factor. Be careful with the sleeve. Not for the sleeve, it's going to survive. It's for you. Okay, you have a bunch of different expressions. Okay, that you have. You have Colebrook expression, you have implicit expression, explicit expression, but we are going to use the expression by Holland, which was a professor here at NTNU. That's the one we are going to use for this course. And the equation says that F is equal to 1.8. You will have it programmed in VBA. And all of that to the power of -2. Okay, so that's the one we are going to use. It's an expression by a professor called Holland from NTNU. And I think it was in 1983, around 1983. And also another, I guess you're already familiar with that, but beware, okay? So I'm going to put this in red so you are kind of awake. Remember, we have two friction factors defined by different people. Okay, one of them is the Moody friction factor, and we have the fanning friction factor. So be extremely careful. We have what we call Moody, or officially it's called Darcy-Weisbach friction factor. Okay. That the definition is, and that's the one that we are going to use in this course. Okay, the shear stress on the wall divided by 1/8 of density times the velocity squared, and we have also the fanning friction factor, which is exactly the same but is 1.5. Okay, so that means that the definition is the F of Darcy is 4 times the F of fanning. Okay, so be careful. Depending on you have to be extremely careful that the correlation that you're using for the friction factor is the one with Darcy. Otherwise, you will have an error in your calculations. Okay, and remember that this is showing this F in a way is okay, delta P divided by density velocity squared is like a adimensional pressure drop. Okay, so you're plotting here is the adimensional pressure drop with some adimensional velocity to try to make it general for every case, for every pipe, for every velocity you have, to avoid having to make one curve for all of them. Yes, so let's go now to the other point I was saying a bit. So oil water flows can be treated, can be modeled, okay, using liquid pressure drop equation. Okay, but there is something extremely important. Okay, in oil and water flows we have the formation of emulsions. Okay, an emulsion is nothing more than a very fine dispersion. Either if you're talking about an emulsion of oil in water, a very fine dispersion, very small droplets of oil in water, or very fine droplets of water in oil. Okay, fine, and the most important is that it's stable. Okay, will you leave it a long time and it doesn't separate? So it can have two ways. One of them I have the droplets of oil, okay, and the continuous media is the water. Okay, or you have the other way, which the continuous media is the oil and the droplets are water. So why do we care? Okay, why do we care about these emulsions? Okay, so if you plot, okay, let's say here you're plotting the delta P. We are looking at a pipe, okay, from 1 to 2, and we are keeping, let's say we have no issues with pressure and temperature. The rate is always the same. Okay, we can measure exactly the rate at local conditions. So here we are saying the rate is the same, okay, constant rate. And here on the x-axis we have the water cut, okay, or not the water cut exactly. The water cut is usually defined with standard conditions rate, okay, but the water fraction, which is the water rate divided by oil plus the rate of water. Okay, if we make experiments, okay, when this one is equal to 0, That means no water. That means pure oil. Okay, here I have pure oil. I will have certain pressure drop, right? Then I say I increase, this one goes from 0 to 1. Okay, I increase, let's say, to 20%. I see something very interesting. Okay, I see that all the water that comes on top, okay, all the water that I'm adding, it's basically is going to look like that. Okay, it's going to look like number 1. I'm going to put that drawing. I'm going to put it here. Okay, but the pressure drop will be higher. Okay, and that process is going to repeat and repeat. Is going to be increasing, increasing, increasing until we will have a very, and depending on the emulsion, depending on the properties of the oil, depending on the amount of mixing, how you are forming that, it will have an increase in the pressure drop that can be sometimes even 2 or 3 times the one of the oil, of the single phase. Okay, a huge pressure drop increase until it reaches a point that is called the inversion point. Okay, and this inversion point for oils is something between 0.4 and 0.6, can be all the way going all the way to 0.7. And then what happens is that it will start decreasing again until it reaches just the pure water. And the thing that happens at that inversion point is basically that the emulsion is going to change from automatically. It finds, it's like it finds the less energy configuration. Okay, here that was the less energy configuration, but then as I start to increase the amount of water more and more and more, it's going to swap. Okay, and it's going to change to another configuration. Okay. It's usually the peak, yeah. Some oils you have a very clear peak, it's like 2 or 3 times. Okay, 2 or 3 times the delta P of the oil, okay, single phase. Sometimes it's much bigger than that. Okay, depends on the oil that you have. So you have to be aware, okay, if you are a production engineer working on a field and you are going to be next class, okay, so you have to be careful, okay, with that point, because if that, what happens with water with time, with the water cut of the field with time, is going to increase, okay? And if sometimes it might happen that if you have a system with oil and water, you're going to pass through that point, you're going to get into trouble, okay? You have made all your calculations for some pressure drop, you're saying, yes, I can produce my rate, trust me, you know, no problem. And then it comes year 5, you start with a water cut of 60%, 50%, okay? You have too much pressure drop, you cannot produce. Okay, so the way we analyze emulsions is we say we can apply the same equation that for liquids, okay? Okay, the Bernoulli equation, Z1, P1, sorry, density, but now density, I have to use the density of the mixture. Exactly, everything is the same. And then I have the losses. Okay, but now on the, so first this density of the mixture is defined as, for every point that I'm analyzing, is defined as the density of the water times the volume fraction of the water plus the density of the oil times 1 minus the volume fraction of the water. Okay, which this is the volume fraction of the oil. Okay. Yes, so that's the first step. But now the second and most important step is this F, okay? Is the viscosity. In reality, the way that they have found to tackle that problem is to say, well, my viscosity, I know the pressure drop will have a behavior like that. Okay, so if I put a horizontal pipe, exactly horizontal, okay, I take away the elevation effect, this density of the mixture effect, but I just look at that curve and I try to generate an equivalent curve for effective viscosity of the mixture. Okay. And it does exactly the same. Here I have the viscosity of the oil. Here I have the viscosity of the water, but I have this peak, and I exactly calculate that viscosity until it gives me the same delta P that I'm measuring. Okay, so that's the way I say, well, I don't know what it is. Is it a mixture of fluid, okay, water and oil? It will have certain characteristics, but I know that to reproduce exactly that curve, okay, I have to use this behavior of viscosity with the water cut, okay, with the water fraction. Okay, so then I have just to make, some measurements in the lab, depending on the crude that I have. And I have to, usually I don't like to use the points, but I use an equation. Some equations that are typically used are, and I don't have them here, but some equations used emulsion viscosity are Brinkman. I don't have it here, and that's very famous, very widely used. And you have another one which is that is called Richardson. Okay, and Richardson, that's the one you're going to use tomorrow. Basically, it says that the viscosity of the mixture is in the left, okay, the left part of the curve. It will be the density of the viscosity of the oil times E water fraction times the coefficient CW. Okay, and to the right, the viscosity of the mixture will be the viscosity of the water times E alpha 1 minus alpha water times CO. Okay, just like you try to tune your results, you try to tune to an exponential expression. Okay, and also on this side, and both sides they will have a different coefficient. That's the expression you guys are going to use tomorrow. Okay, but of course it's very so you need to have measurements like our guest lecture today. All of these equations, they look very nice, they can allow me to make calculations, but they have to be based on measurements, okay, because it has very big changes from system to system. Okay, any question? No? Yes.
Sorry, I'm away of. We were trying to check the pressure drop versus water cut. I mean, how do we know that? I mean, the graph is that way, that the pressure drop increases after the.
Just doing experiments.
Okay, so it's modeled already.
Yeah. So you have to make, like I told you, you put a pump, you measure pressure at the inlet of the pipe, pressure at the outlet of the pipe, and you start changing the water cut until you see. And sometimes it might happen that your fluid just behaves like just separates. Okay, that's also something that might happen, and you don't get this emulsion effect. Okay, you don't get this peak. You just say that the two of them flow like a layer. Yeah. But sometimes you get that effect, that mixing effect, and then you create emulsion, and then you have that peak in between. Okay, but that's only by doing measurements on the fluid to see if. Sometimes you can also make it on a beaker. Okay, you make on a beaker, you mix two ratios of the. Okay, for example, you mix water, you mix with oil. Okay, you put a propeller inside, you mix it very well. Okay, and then you measure the viscosity of the mixture. Then you use another fraction, and then you measure it on the beaker. Okay. The thing is that I don't want to go too much, but the beaker should simulate the same shear that you have in the pipe. Okay, the same amount of mixing that you have in the pipe. Sometimes, if you use, for example, a very high shear rate, a very high rotational velocity, you are actually mixing it too much. Okay, so maybe the viscosity you're going to get is not going to be representative of the same one that you will find on the pipe, in the pipe. Yep. Yes.
How different would this response be if it's a vertical pipe, not a horizontal? Because then the gravity would also happen.
Yeah, but an this is just a way to tackle this guy in emulsion. Okay, so how do we model emulsions? After you have in a vertical pipe, the only effect will be the effect on the density. Okay, but if you think in terms of the formation of emulsions or not, in a vertical pipe you don't have the gravity acting. Okay, so you have a bit more tendency to form emulsion. Okay, than in a horizontal pipe. Yes. Okay, now to finish our session today, I want to talk very briefly about, and that's the whole story about emulsion, single phase liquid is just to introduce to the term to the a bit about electric submersible electric. Okay, electric submersible pump, ESP. Exactly the same component that I had for the compressor to bridge available and required. I want to deliver certain rate. Okay, in that case I make my plot. Okay, remember I have my well, my PWF, my wellhead. Okay, and I plot from the reservoir, sorry, PWF versus Q of the well, and one is going to look like that, one is going to look like that, and I want to produce for that particular field that, and I need something at the bottom of the well to make that, to bridge that difference. Okay, and for that is called an ESP. ESPs, they yeah, so that's yeah, I think I will put the face of the guy that always puts makes you a bit more serious our conversation. So that, okay, so that I forgot to show that image. I forgot to show that image. Okay, that's that we made here in the lab. That was a student working with me 2 years ago, and that's a mixture. If you without just water and oil, you leave it some time and it separates. But this is, you do that experiment that I told you. You rotate and you mix it in the beaker, and that's actually quite stable. They could stay there for 5 hours without separating. Okay, it looks like almost like this. How to say, mayonnaise, the one that you use on the bread. Okay, I forgot to mention that. Okay, so let's put this serious guy to put some seriousness to this class. Okay, was a Russian immigrant that came to Oklahoma and had this great idea. Actually, pumps were already used many other industries, many other places, but the big idea that he had was how to find a way to package that pump and to put it inside the well. Okay, and it will last. It won't broke after a short time. So let's put here the name of the inventor of the ESP, and actually the whole community is in depth to this inventor. I'm not sure how to pronounce it, so I leave those that speak Russian to help me. Arutunov. Okay, and you need actually the way the pump is. So there you have one box that first you have here the pump. Okay, we will see now it's not one pump, but it's actually a collection of different stages. You make the process in different stages. Then you have the pump intake, or sometimes you have a gas separator. Okay, let me put it like this. and then you have this intake to the pump. And then below you have the motor. First you have, well, the seal, but let's put it just the motor. Okay, and the fluid, let's say our fluid, that's our well that we have here, and our fluid is coming from the formation, is supposed to cool the motor. Okay, and then it's supposed to enter through here. If it has any gas, by any chance some gas comes out of solution, the gas is just flushed to the annulus. Okay, where if I have an open annulus, it's going just to percolate and bubble up, okay, and be produced through the annulus. And then you have the pump section. Okay, we are going to focus not on exactly how it looks like, but just the performance. Okay, just exactly the same. We have that delta P. We have to see if it's feasible to produce that rate or not. Okay, so here is the way it looks like. Again, I'm going to put here a figure. And that's the pump has many stages like that, okay, that are collected one, and here we have one on top of the other. So that's the rotating part, and that's the part that is shown there in the figure. Okay, the fluid comes through this ring region, and then it's accelerated, then it's flowing outwards. Okay, but the other stage is going to look exactly the same, like this one. So you have to redirect the fluid that comes outside, again, back through the radial position, and then oriented exactly to the inlet of the next stage. Okay, so it looks something like that. Yeah, so here you have exactly that. You cannot see it very well, but that's the diffuser. Remember, I told you, just like in a compressor, you have acceleration giving kinetic energy to the fluid, and then you recover. You actually transfer or convert part of that kinetic energy to pressure energy. Okay, and then the process is repeated, one and the next and the next. Okay, let me try to make a primitive drawing. So you have okay, that's the rotating part. Then you have the shaft, which is giving the rotation to that impeller. Then you have the same thing here on the other side. Okay, so the fluid enters through here. That's the part which is rotating. These two are together. Okay, and that's one part that we are going to look tomorrow. That actually these two are held together by something called a key. Okay, that allows to give rotation. And then after the fluid is exiting, the fluid here is just coming. Okay, so the fluid here is just going through this passage. Okay, and then the fluid has to be redirected to the passage of the next pump. So for that we use like something like that. Okay, and here I'm missing the wall, but so you got the idea. So what is the performance of how is the performance of one stage? If we look at one stage, how is the performance of that? Remember, we always want to start with delta P versus rate, right? Because what we are going to get from here is basically delta P versus rate. So how is it going to look like? Exactly like an available pressure curve. Okay, it's giving energy, so it's going to look like that. Okay, If you can see that the energy is somehow conserved, the energy in the power, hydraulic power in a pump, that's not pressure, that's power, is roughly delta P times Q divided by the hydraulic efficiency and the mechanical efficiency. Okay, so if you are using high, that's limited, right? The engine I have, the motor I have on the pump. So if I use high delta P, then the rate has to be smaller. If I use a low delta P, then the rate can be higher. Okay, you have this, and why it's not exactly a straight line? The efficiency. Okay, the shape of the efficiency basically is like this. Okay, this hydraulic efficiency. Now the thing is that that's for one stage, and basically you cannot breach that delta P with one stage. Okay, so if one stage looks, every stage has to handle the same rate. Okay, but they have to handle much, the height has to be much less. So two stages will be like that, three stages will be like that, and so forth. And at the end I make my pump just by n times the delta P of a single stage. Okay, and as simple as that, when I select the model, I say, well, I need this particular delta P. Okay, the delta P required will be the number of stages times the delta P of one stage. But because of that process that I have to take out the fluid, bring it back, take it back, bring it back multiple times. Here I have a lot of friction losses. Okay, so I usually have a factor that is called the pancake effect, pancake factor. Okay, such that I say, well, if you put all of them one after the other, that's not going to give you exactly just multiplying the number of stage times the curve of one stage. Okay, I have just some losses that I have to take into account. Okay, so if you already have one pump that delivers something, here will tell you how much do you need. And that number, it's something that can be between 50, 30, all the way to 100. Number of, small number of stages that you put, one after the other. Okay, so I think that's enough for today. So tomorrow we are going to continue. You're going to have an exercise, okay? But we are going to continue. I have to give you how the curve looks like, what are the operational constraints, and do exactly the same we have done for the compressor. Okay, what things do we have to take into account when estimating, considering that we have a pump in our production system. Okay, any question before we close? No? Okay. See you tomorrow.